Hello future engineers, today we're going to have a look at electricity, the very basics of electricity. One of the things you'll have to do on your course is to put together a small electronic circuit as part of your gravity racer buggy. Okay, this is a small circuit with some flashing lights. But in order to do that, it would be a good idea to have a grasp of what electronics is. Okay, so we can start by having a look at the quantities, the main quantities of electricity. So by the end of this lesson, I'm hoping that you will have a reasonably good understanding of what each of these three terms mean. But in order to begin on that journey, we need to have a look at what electricity actually is. So if I pop the board up a little, all material everywhere in the universe is made from atoms. So I'll draw a picture of an atom. So in the centre we have a nucleus. Inside that nucleus there are two smaller particles that make the nucleus up. They are called protons. So I've just put a P in there, I hope it turns up on the video. And neutrons. So there's an N for neutron in there. Orbiting around the atom, around the nucleus, you have a tiny little particle called an electron. And this is the particle that we're interested in. Now, electrons are negatively charged. We'll come back to what charge is just shortly, but I just want you to get a picture of essentially Rutherford's image of what an atom is. So the protons are positively charged. And for our intents and purposes, we're not really interested in the neutron. Okay? So, we have the word charge. What is charge? Charge is essentially a way of measuring the electric energy that a particle can have. It can be positive or it can be negative. So positive, negative. This electron here, the negatively charged particle, is the particle that is electricity, if you like. Electricity is the movement of these particles. Okay? So the movement of charge on mass is electricity. That might not be very clear, but I'm going to draw a few atoms now, all in a row, just to let you see what happens. So, if we zoom right in, here's an atom, second atom, third atom, fourth, and fifth. Now let's say that each atom has an electron on its outermost shell. So I'll draw it with a little cross, just so as we can see them. Little X. So those are the atoms, each with a little electron orbiting around it. Now let's say I try to introduce another electron over here. Let's say I have a battery. Duracell battery. No sponsorship. If I create a circuit, so a route all the way, put a switch in, just so that we can say we've got a circuit. And we imagine that these electrons are in, say, a piece of copper, for example, a copper wire, but we've zoomed right in. We've zoomed so far in that we can actually see the atoms with their orbiting electrons. If I try to add another electron into the system, this first atom now has 2 electrons. It doesn't want to have 2 electrons. It wants to be a neutral atom. If I scroll back up here, every atom wants to be in a state where it has the same number of electrons as it does protons. That makes it neutral. It has no extra charge. It doesn't have any extra positive charge. It doesn't have any extra negative charge. It wants to be balanced. So, if we go back to this little drawing, what I've done is, I have introduced another electron here. This atom wants to be neutral. It doesn't want to have an overall charge that's either negative or positive. It wants to have the same number of electrons as it does protons. So what does it do? I've given it 1 extra. Well, what it has to do is it has to send one of its electrons over here to the next atom. So we'll draw the electron in there. This electron is happy now. It has neutrality. It has no charge. But the problem's only shifted along. Now this atom has 2 electrons. So what does it have to do? Simple. It has to give up one of its electrons to the next atom. Everything's fine now. At this stage, this atom is now neutral. The problem has shifted across here, and this will continue to perpetuate across the length of that material. It gives up its atom to the next one, forcing that atom to give up its electron to the next one. And so, this electron spots itself all the way around the circuit, only when the circuit's closed. We need to close that switch so that there is a complete loop, a circuit. And when that circuit's made, the battery will push these electrons into the circuit, and they will jump from atom to atom until they make it all the way to the other side of the battery. So you might be wondering how the battery manages to do this. Well, there's a chemical exchange going on in here, a chemical reaction that causes electrons to flow. But perhaps that's for a different lesson. I've used the word flow of electrons. That's exactly what we have. We have a flow of current. In one direction. Batteries supply direct current electricity. It means that if you hook a battery up to a basic circuit like this, the electrons will only flow in one direction. Let's not worry about what that direction is just now, but this is the process by which it happens. So, current. It's all very well speaking about having a current, but we need to think about terms that we can use to describe current, to allow us to put it into mathematical formula. We won't do too much of that, but you need to know this terminology. So the thing itself, the flow of electrons, is current. The unit that we use to measure the current is the ampere. Commonly, that's, we use a shortened term for that, we just call it the amp. So if you can't remember ampere, not a big deal. Pretty much everybody just speaks about amps, but it's not anything different. So we'll take out the air, we'll just call it an amp. When we say we have 2 or 3 amps worth of current, we'd maybe write it like this: 2 amps. We also give current a symbol for putting in a formula, and that symbol is the letter I. Why is it the letter I? Well, usually we want to know how strong a current is, and we speak about how intense that current is. So I for intensity. Yeah? So we have a current of 2 amps. I could say that's a reasonably strong intensity. We're not talking about lots of different things here. They all relate to one another. Current measured in amps. If you measured 2 amps, you would write it like this. And if we were using current in a formula, I would say I equals 2 amps. That's the first thing. That's one of these terms out of the way already. The next one to look at is probably the voltage, because we need to know why current wants to flow in the first place, or is made to flow. Notice that current's very much like water. It's the same thing. Water moving through a river in a current. So you have something that's moving, it's the electrons. What causes it to flow though? As I said, systems want to be neutral. Electrical systems want to be neutral. They want to have an equal distribution of charge throughout the system. And when they find that neutrality, charge stops flowing. Okay? When I say charge, I'm talking about individual electrons. Let's imagine you have a small jar, and in that jar this is the jar, we can put so many electrons. And I'll draw them in, just as spots. So in this jar we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 electrons. I could say that I have a small packet of charge there. Is this right? Small packet of charge. Some charge, we'll call it. Charge, incidentally, gets the symbol Q, and it's measured in coulombs. Which gets a capital C. It's named after a French chap called Coulomb that studied this. Don't worry about that. Okay? But let's just say I have a jar with some charge in it. Now over here I'll put another jar. Now this jar only has a little charge in it. Hardly any charge at all. If I create a circuit by, I don't know, putting a piece of copper wire, will charge flow? Will electrons flow? Not yet. There's no circuit. We need a circuit. So I'll take another wire from here. We'll put our switch in. Switch is a handy thing to have. So what do you think happens when I close the switch? Take a moment just to think about it. Pause the video. When I close the switch, I have created a circuit. Now charge will flow in this direction until we have the same amount of charge in both jars. One, two, three, four, five, six, seven, eight, nine. 1, 2, 3, 4, 5, 6, 7, 8, 9. This system no longer has charge. It is now neutral. The difference in the charge at the beginning is what we call a voltage, or we measure as a voltage. When there were many electrons here, there was what we call a difference in potential, a difference in electric potential. Lots of electrons, no electrons. Electrons will flow from a region where there is a lot of charge to a region where there is hardly any charge until we find that neutral balance, like a seesaw. That difference between the amount of charge at, say, point A and point B is the voltage. So I'll give you a sentence to cover voltage. I hope it appears on the board with this lighting conditions. A voltage is a difference in electrical potential. Let's see if you can figure out which way charge will flow in these little diagrams. and one more. Pause the video and have a think about it. Right, for those of you who said that charge would flow from A to B, that's correct. The current flows from A to B because we have a difference in potential. There are more charges here than there are there. So we have a voltage. Is it a particularly large voltage? Well, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 charges and none at all. I would say that's a pretty low voltage. Low voltage, charge moving, as a current. It's low voltage because there's not much difference in potential. You know, we've got no charge here, charge of 10 there. I'm making these numbers up. Let's have a look at the second one. What direction do you think the arrow for the current will flow? What direction will that charge be moving? If you said that direction, you were right. There's more charge here than there is here. So electrons will flow, charge will move from B to A. 1, 2, 3, 4, 5, 6, 7 versus 3. Charge is going in this direction. Again, there's hardly any difference in potential. So not much difference. In potential. Low voltage. Is charge flowing? Is there a current? Yeah, there is. It will continue to flow until we have the same number of charged particles, electrons, at region B and A. Now, for the last one, what direction, first of all, will charge flow? What will be the direction of the current? If you said B to A again, you were correct. Obviously, there is a higher electric potential here. Much more charge than there is here. I'm not going to count all of those. There's a lot of electrons sitting there ready to move. And there's very little. In fact, there's only one here. So this is a bigger potential difference. That means it's a higher voltage. What do you think that'll do to the current? Well, I can tell you, these two currents are very small because there's no real pushing force. The voltage pushes the current. The bigger the potential difference, the more force there is making the electrons want to move, moving that charge. So these two might be measured in milliamps. And a milliamp is 1/1000th of an amp. Over here, so the first two are small currents. So over here, we have a big potential difference. That means a bigger voltage. We call it a larger voltage, a higher voltage. So this current here is going to be big compared to these. I'm going to call it 5 amps. Again, this is a made up number, but 5 whole amps. Just examples, just pictures, just to get you the idea. So, voltage sometimes it gets the symbol E. I think we'll just stick to using the symbol V though. So voltage, symbol V, whoops, and it's measured in volts, which is also a V. That's handy. So current, amps, that's the unit. We would write it 2 amps, and we would say that the symbol I for current, intensity, 2 amps. Voltage, I might say I have a voltage, so I'd say something like V equals 20 volts. Again, not a calculated value, just a number I used to show you how it would be written down. Remember I said that sometimes we would have that E, and I spoke about force. The E really stands for electromotive force. We usually tend to write voltage though. And remember, big potential difference, same as having a higher voltage. It's exactly the same as having a higher electromotive force. This is an example of the electromotive force. Electron comes in, forces another one out. That's how the electromotive force works. So we've only really got one more thing to look at, but I'm going to have to clear the board a little bit. So, resistance. How does that work? Let's think of the size of pipe work, like in the plumbing in your house. If I have a really thin pipe and I attach it to a tank of water, and we'll say there's a valve in there that we can use. Okay? Here's the end of the pipe. What happens when I open the valve? Turn the valve to the on position. You guessed it. water. Water will flow. What happens if I make that pipe really, really super narrow? Try and draw a really, really, really super narrow pipe. Will the same amount of water flow as it could before when the pipe was wider? No. What you're going to get, instead of a flow, is just drips. Essentially, this is what resistance is. If you think about it as being how able current is to flow through a material. Resistance is governed by a couple of things. So one, the material. And that is down to how many electrons that material has in its atoms that are free to move around. You know? If it doesn't have any of these free electrons, then we usually find that that material is an insulator. It's very difficult to pass electricity through it, to pass a current through it. Okay? So the material is important. The dimensions of the conductor is the opposite of an insulator. It's just a word that we use to talk about materials like all metals which will allow electricity to pass through them because they have plenty free electrons. So the material, does it have free electrons? If the answer is yes, you should be able to pass a current through it. The dimensions of the conductor, the size of the pipe. If I have a conductor that has, let's say I wanted to run a circuit like this. I'll draw the symbol for a battery rather than actually drawing a big battery. So this is just the symbol for a battery. If I want to place a battery there and cause a current to flow through this material, the area is important. The bigger that area is, the more atoms there are, so the more free electrons there are to be moved around. So if you make that area bigger, then you are reducing the resistance. You're allowing more electricity to flow in the form of current. So, big area equals low resistance. Instead of writing resistance, I'll give it its symbol. It's the first one that has a funny symbol that isn't a letter of the alphabet. The symbol is omega. Resistance is measured in ohms. If it's got a small area, it'll have a higher resistance. High resistance. Omega. Ohms. I'll write ohms. Another capital letter, so it's named after some chap called Mr. Ohm, who studied this and came to this conclusion. So, out of the two areas of that piece of material that I'm about to draw, try and guess which one has the highest resistance. So there's the area of that face. We're going to pass current in here and round a circuit all the way back round. We'll call this A. And I'll draw your alternative possibility. Call it B. So have a think. Which one of these two materials, simply because of its size, its dimensions of they're conductive materials, simply because of the size, the dimensions, which out of those two do you think will have the biggest resistance? Well, the answer is B. B has a larger resistance than A because B has the tiny little area. Small area, high resistance, measured in ohms using the symbol omega. So if I wanted to say something about the resistance of this material, just take these out just now, I could say that my conductor has a resistance of 25 ohms. So I could say R for resistance equals 25 ohms. That's how we would write that. The resistance is equal to 25 ohms. There's something else that governs the resistance though. Just take this drawing out. Take this out. You can always rewind the video. So, we got what's the material made of? Does it have free electrons? If it does, it conducts. If it doesn't, it's an insulator. We've got the dimensions of the conductor. One of them we just looked at was the cross-sectional area. Cross-section is just the area of that face if we were to slice it and measure the area. The length of the resistor is important as well, or the conductor rather. So length. Whoa! Let's draw that properly. Length. If you walk up a hill, you get tired. If you try to lift something heavy over a long distance, you get tired. If you go swimming, eventually you get tired. The reason you get tired is because everything uses up a little bit of energy to get stuff done. It's exactly the same with electricity. When I try to pass current in the form of moving electrons through any conductive material, there has to be some work done to make that happen. Now, in electronics, with electricity, we lose a bit of efficiency when we try to pass through longer distances. So if I have a conductor that is, we'll call it from there to there, 1 meter. We'll call this situation A. And then I'll draw something over here, not to scale, but I will try and make it a little bit bigger so that you can see. We'll call that situation B. And we'll say that that is a kilometre, 1,000 metres. One metre in length. We're talking about an electrical conductor, piece of wire in a circuit. Again, you need that circuit. And I want to move some current through it using a voltage. Okay? This one, the one that's only a metre long, that's going to be able to conduct that electricity reasonably easily. It's going to have a low resistance compared to situation B. Situation B will have 1,000 times more resistance than situation A. The wire is 1,000 times longer. It's a kilometre. So for example, if that's about a metre, say that's around about a metre from the edge of the board to here, a kilometre is maybe from the Kingsway campus to the roundabout at the top of Old Glams Road where I believe it's the Cleppington Road intersects. That's probably about a kilometre. So obviously it's going to have a much higher resistance. So the length is important as well. So longer lengths equal higher resistances. I'll just put high ohms or high resistance. Short lengths low. There's another factor as well, one more factor. Temperature. If I take any object, well, imagine a piece of copper in the form of a bar, okay? Just a lump of copper. If I apply heat to it, what I'm doing is I'm giving it energy. So when I'll rub this out just for a moment. In fact, here's a model of a helium atom. Okay, I was going to draw a picture of an atom, but it's better to show you. So, nucleus consisting of protons, neutrons, and we've got a couple of electrons. There's obviously no sticks. You know, the sticks are just to show you that the electrons are in orbit around the nucleus. So, when I apply heat to this, in the form of heat energy, right, what I'm doing is, the energy actually sort of agitates the electrons. The energy agitates these electrons. It makes them fizz, if you like. It also causes this nucleus to vibrate a little bit more frequently. Okay? If I keep on applying heat, it really starts to shake. The electrons whiz around. They get more and more agitated, more and more agitated. This is what happens when you add energy to any system. So, more energy, more heat. Electrons become fizzier, fizzier, fizzier. It's the same if we have a conductor and we try to increase its temperature. Its atoms start to fizz, they become more energetic, the electrons become more energetic, and they really start bouncing off of atoms and hitting other atoms and moving around, and it becomes very chaotic. That makes it more difficult to pass an electrical current through, because that atom that I add to the situation, it doesn't join this atom and cause that one to fly off and hit the next atom nice and uniformly. What happens is, I add my current in the form of charge, electrons, into the system, and because everything's bouncing around inside this material, that electron that's kicked off has to travel around a wee bit before it bumps into the next atom. So eventually it'll bump in, and then that atom will give up one of its electrons, and that'll fizz around for a while, and it'll bump into the next atom. So this process, this movement of electrons, it becomes more difficult when the temperature comes up. So let's say high temperature equals high resistance in ohms. Could I put that R across here as well? Resistance is measured in ohms. Low temperature equals low resistance, measured in ohms. You may have heard in science fiction programs, or maybe even in some documentaries about electricity, that we speak about superconductivity. Well, that's an actual thing. What we try to do is we take an electric circuit and we reduce its temperature down so low that the resistance becomes negligible. And that means we can have a far more efficient system that doesn't use as much energy. Okay. So that was the basis of electricity. These three quantities that I've shown you can be linked together in a formula. And if I said, probably do this in black, you need a voltage of 1 volt to move a current of 1 amp through a resistance of 1 ohm. That kind of ties the whole thing together. Pushing force, like a lot of water stored in a tank, pushes a current, like the water in the pipe, through the pipe. You need a voltage of 1 volt to move a current of 1 amp through a resistance of 1 ohm. And it just so happens that V equals IR. Voltage equals current times resistance. If you're not familiar with two terms sitting next door to each other, we always say that we multiply them. Voltage is measured in volts. The intensity of the current is measured in amps. And the resistance in the circuit, or the conductor, is measured in ohms, which gets that symbol. Voltage in volts. Current in amps. Resistance in ohms. O Named after an Italian called Alexandre Volta. Named after a Frenchman, can't remember his first name, but his second name was Ampere. I think it might have been Pierre Ampere. And I believe this chap was a German, Heinrich Ohm or Henry Ohms. I can't remember the first names, but the second names are all surnames of people that studied this stuff and figured all this out. So, watch this as many times as you need to. I would watch it once all the way through. Then I would maybe consider taking some notes, trying to write it out in your own words. There are years worth of reading materials online for this. Just Google these terms. Remember though, cross-reference everything you get from Google. Some people don't necessarily explain it the proper way. This is the proper way. Try and learn it, okay? It's useful to know.